Students, today we are going to finish up this course by discussing the ternary phase diagram of silicon dioxide, aluminum oxide and magnesium oxide. Before that, I would like to take about few minutes to discuss the stainless steel phase diagram, which is basically nothing but between iron, chromium and nickel. As you know, stainless steels are actually steels with very low carbon concentration. Major alloying elements are basically carbon, so basically iron, chromium and nickel. And for a typical stainless steel like 18-8, we add about 18% chromium and 8% nickel. So therefore, almost about 75% is iron and rest of the things are basically alloying elements. So before actually for any ternary phase diagrams, we need to know the binaries. This is something which you have probably seen all my lectures. First thing we do always to consider the binaries between the components. So in the iron, nickel and chromium system, there are three binary systems. Between iron and nickel, you know, there is a continuous solutions existing from nickel rich end to very close to iron, but at about 4.6% nickel as you see here, and 1517 degrees Celsius temperature, there is a peritectic reaction. Although it is not clear, it is like this, very small peritectic reaction taking place. So this is how the phase diagram looks like. Okay. So this is what I am talking about. This is a peritectic reaction existing at that temperature. This is nothing but delta plus liquid giving to gamma. Same as iron carbon phase diagram also, but it is very clear. Another important thing in the iron nickel phase diagram is that the gamma phase, which is the FCC iron nickel solution, is spread or is basically exists over a large composition range. Alpha is basically stable for small composition range, as you see here, between 1 to 4% at 600 degrees Celsius temperature. Otherwise, it is basically gamma is getting stabilized because of iron addition. So that is for the iron and nickel phase diagram. On the other hand, iron chromium phase diagram is, it's quite a bit different. First of all, iron chromium both having BCC crystal structure, and because of that, solution from iron rich end to chromium rich end. That is what you see here, a funny isomorphous phase diagram existing from iron end to chromium end. Chromium melts at much higher temperature, 1907 degrees Celsius temperature. Another important feature is that instead of in iron nickel system we have seen gamma getting stabilized, but here alpha getting stabilized, gamma forming a small loop. That is because chromium is basically having a BCC structure. That is the very salient feature. And last thing which is important is that chromium also very close to about 50% chromium, it forms an intermetallic compound known as sigma phase, and this is what is shown here. So alpha basically seems to undergo spinodal kind of decomposition, forming alpha plus forming sigma, alpha plus sigma or sigma also, correct. So therefore the behavior between iron with nickel and chromium are distinctly different. That is what I have seen. Now let us look what happens to chromium and nickel. Nickel chromium phase diagram is very simple as compared to iron nickel and iron chromium. Why? Because there is only one eutectic reaction here at 1350 degrees Celsius temperature. You see here, an eutectic is between nickel solution and chromium solution, correct. And at temperature about less than 590 Celsius temperature, some kind of order compound gamma prime forms here. Other than that, there is nothing much. So if I put these things together, you will have a phase diagram which I have already shown you, but I am going to draw it and discuss with you. Let me see on the board if it is possible. Let us see that. Okay. So basically first I will draw this triangle. The reason I am drawing this is because all these lectures I try to show you the how to draw this. If you follow my way of drawing, then you can draw these things very easily. So you know that between iron and chromium there is isomorphous phase diagram. So chromium melts at higher melting temperature, I should draw it with a color chalk, otherwise things will be not clear. Okay. So, that is between iron and iron and chromium, lower temperature, although it forms a loop, but I am not drawing it here. And between chromium and nickel we have a eutectic things forming. Nickel measure 1556 degrees Celsius temperature, so we should increase this little bit. Correct. And then between iron and nickel, you have a pedictic reaction to the iron end. That is, these are the three binary phase diagrams. So, this is 1556, 1538 and this one is 1907. Correct. So, what actually happened if I have these three important phase equilibria existing at high temperature? What we can do is that we could clearly see that because of presence of these two important reactions, one is eutectic, another one is peritectic reaction, the phase equilibrium will be decided by these two, completely decided by these two. So, let me just draw and show you how it will be decided by these two. Basically nothing but connecting these two things with this. This is let me draw it. Okay. And so, you can actually form a triangle like this. So, basically the three phase equilibria extends this binary eutectic will be extended this is extended inside this ternary phase field. That is how the phase diagram looks like, correct. So, as you see here, so therefore, depending on the alloy composition temperature, ternary alloy either will slide down to this eutectic or the peritectic reaction, that is what it is. So, let me also tell you the temperatures of the eutectic and peritectic reaction. The eutectic reaction takes place at much lower temperature 1345 and peritectic reaction is taking place at high temperature, this is 1517. Okay. So, that is why the whole equilibrium basically is dictated by this eutectic reaction mostly, mostly. So, this is what you should remember. The stainless steels actually are iron rich compounds, so they lie somewhere there actually. So, they actually in most of the cases undergo the peritectic reaction, that is what you should remember. But there are different types of stainless steel. The stainless steel contains little bit higher amount of nickel, then the peritectic reaction usually happens. In fact, that is why the most of stainless steel, the basic problem is the welding. In case of welding, the stainless steel actually undergoes this peritectic reaction and forms a lot of cracks. So, otherwise this phase diagram is very simple, but on the other hand, if I take alloys which are chromium rich or this side chromium rich, so they are very easy to handle, but normally God does not give the easiest thing in the world. So, that is why actually here the most of the alloys which are stainless steel type will be undergoing the peritectic reaction, and that is what is the problem. So, I guess it is very clear from the binary phase diagrams what is going to happen. So, equilibria is basically dictated, as I said, between it shows a monovariant reaction here, because it is a binary eutectic getting extended into the ternary. So, monovariant reaction, and the monovariant reaction curve monovariant liquid curve descends below the eutectic chromium nickel eutectic isotherm, peritectic isotherm of the binary sides and terminates actually. Basically, if you look at this board, the the monovariant eutectic this equilibria, which is known as written on the book, it basically extends from the peritectic to the eutectic. It starts from peritectic and descend to the eutectic temperature, ends there. That is what is the situation happens. Other than that, nothing much happens in these alloys. Okay. So, now I have been giving you some idea about that. Let me just go into the last important phase diagram between silicon dioxide, aluminum oxide and the magnesium oxide. Okay. So, before telling the actual ternary phase diagrams, let me just explain you the binaries. If you really see here silicon dioxide aluminum oxide phase diagram, what do you have? You have to understand two things. One, you have a mullite. These binary phase diagrams I have already discussed you in some lectures. Okay. You have an intermetallic compound or intermediate compound known as mullite, which is nothing but 3Al2O3 2 SiO2 compositions, and on the both side of that compound there are two eutectic reactions. That is the funny part of it. What is the first eutectic reaction? This eutectic reaction is like this: liquid reacting with liquid transforming into SiO2. This SiO2 will be cristobolite. You know, silicon dioxide exists in the quartz, cristobolite, tridymite, different structures at a function of temperatures, plus mullite, correct. You can see that. And then we have another eutectic reaction. We have another eutectic reaction, that is this one. Here liquid reacts, liquid forms mullite. It says mullite solution plus alpha aluminum oxide, correct. That is what it is. And other than that, there is nothing much. So, that means what the whole phase diagram is divided into two parts, one eutectic between silicon dioxide and the mullite, otherwise mullite and aluminum oxide. Okay, that is all. And remember this one, this mullite is basically a congruent melting compound which forms at higher temperature. The magnesium oxide, aluminum dioxide, magnesium MgO and Al2O3 phase diagram is also very simple. You have a two eutectic reaction here also. What are these two eutectic reactions? This is the one eutectic reaction. You see here eutectic reaction is like this. It is from MgO solution plus spinel. What is spinel? MgO Al2O3. Many cases it is written as MgAl2O4 or spinel, right. This is the one, and in between you have a spinel formation. That means the phase diagram between MgO Al2O3 and SiO2 Al2O3 has similarities, and this another eutectic reaction which is happens at high temperatures. This happen actually about 2000 degrees Celsius temperature, and this reaction is a liquid going to MgO Al2O3 or spinel plus Al2O3. Okay. This is spinel actually, and in between you have this compound forms. That is about the MgO and Al2O3. What happens to the SiO2 and MgO? This is a little bit complex, but do not get afraid. Here you have basically three reactions. On the left side, which is the silicon rich side, which is the magnesium rich side, you have basically eutectic reaction here taking place. So, you see 1888 degrees Celsius temperature, and this eutectic reaction is what? Liquid going to MgO plus MgO solution plus something known as phosphorite. Okay. What is phosphorite? Phosphorite is Mg2SiO4. Remember, there are many silicides exist. One of the silicide is olivine, other one is phosphorite, codiorite, and this is known as phosphorite. Correct. And then we have another eutectic reaction taking place on this side. This is the eutectic reaction, and it is written actually eutectic reaction is between silicon dioxide plus magnesium silicate MgSiO3 actually. So, therefore, but in between there is a peritectic reaction here, this temperature 1558, there is peritectic reaction here actually, and this peritectic reaction is like this: L liquid plus phosphorite phosphorite Mg2 SiO4 going to N-statite. N-statite is basically MgSiO3, same thing this one, this is known as N-statite. Okay. So, these are the binary phase equilibria. Again I go back, if I tell you again. So, in the simple silicon dioxide aluminum oxide Al2O3 phase diagram, there are two eutectic reactions on the both sides of mullite. One is silicon dioxide plus mullite, other one is mullite plus alpha Al2O3, and MgO Al2O3 phase diagram has also two eutectic reaction. Again it is lying on the both sides of the spinel compound MgAl2O4, and one is the liquid going to Mg solution plus spinel, other one is going to Al2O3 plus spinel. The little complex thing is basically this silicon dioxide Mg or MgO silicon dioxide phase diagram. You have a eutectic reaction on, again on the both side of this compound called N-statite. There are two eutectic reactions. Okay. One is going to MgO plus MgSiO4 or phosphorite, other one is MgO SiO2 plus MgSi3, and third one is basically the eutectic reaction, a periodic reaction forming the N-statite or MgSiO3. Now, if I put these things together, this is what the ternary phase diagram will look like. Ternary phase diagram is again consisting of, there is a separate phase. Okay. Remember, I will first let me mark it. Periclase is basically in a binary, periclase is what? MgO solution, correct. Spinel I told you. Okay, let us first discuss the binary compounds. SiO2 MgO. So, between SiO2 MgO you have phosphorite. What is phosphorite? Forgotten. Phosphorite is Mg2 SiO4, correct. This is phosphorite. What is N-statite? MgSiO3, correct. And on this this side between MgO and Al2O3 you have spinel, which is the most important compound which you have seen, MgO Al2O3, correct. And on the Al2O3 spinel side you have mullite. What is mullite? Mullite is 3Al2O3, 2SiO2, correct. These are all the binary compounds existing. What are the ternary compounds existing? Okay, obviously one is periclase. Periclase is very large solution limits of MgO. Periclase is nothing but an MgO, right. In fact, in the literature MgO is always termed as a periclase, Al2O3 is always termed as a corundum, alpha L3O3, and silicon dioxide can exist in cristobolite or tintinnite state. Okay. So, as you see here, there are three solutions. Let me tell you, one is periclase, other one is cristobolite, third one is corundum. Spinel actually is a very stable compound, and in fact, this formation of spinel is stabilized by MgO additions. Remember, this is basically this what do I say? This is basically liquidous projection of these phase diagram. So, this is the region where the spinel is very stable. Okay. So, you can see here it is stable for large Al2O3 composition range, also it is stable for large MgO the SiO2 composition range. So, SiO2 addition actually increase the stability of the silicon spinel. Then you have a phosphorite. Phosphorite basically is a binary MgO SiO2 compounds, but addition of aluminum oxide Al2O3 actually stabilize a phosphorite. So, you can see the phosphorite is getting stabilized here in this part of regions. N-statite is basically stable for a small composition region, and there are few what do I say, few important ternary compounds. Let me just discuss. One is a codiurite. What is codiurite? Okay, codiurite is 2MgO, 2Al2O3 and 5SiO2. This is a ternary compound. Okay. And another one is called sapphire. Sapphire is basically aluminum silicon compound. Let me see what is its composition. Sapphire, shall I write somewhere? Yes, sapphire is basically 4MgO, 5Al2O3 and 2SiO2. This is the second one. Tridimide is nothing but a solution of silicon dioxide, MgO and Al2O3 stabilized at higher temperatures beyond 1700 degrees Celsius temperature, and that is all actually. So, these are the different phase fields, and these are the liquidous surface projections as you see here, correct. So, as you know here that this coturides actually forms by an eutectic reactions, correct. What are the eutectic reactions basically? Okay, there are many reactions which I should write down here. There are actually several reactions, 10 reactions. The first important reaction here, okay, is the eutectic reaction. This is taking place at high temperature 1710 degrees Celsius temperature. It leads to formation of the periclase plus 2 MgO SiO2. This is nothing but MgSiO3 plus MgO Al2O3 spinel, correct. This is the ternary eutectic reactions. So, that means what? These binary eutectic reactions what you see is extended, one of the binary eutectic reactions are extended inside the ternary, and this happens somewhere here actually. These are the two peridactic reactions and this is the eutectic reaction. I think this one is what is this one, correct. Then you have a couple of peridactic reactions, not a couple, about 1, 2, 3, 4, 5, 6 peridactic reactions, right, 6 or 7, 6 peridactic reactions, okay. And these 6 peridactic reactions actually are 6 or 7, let me see, 6 actually peridactic reactions, and these peridactic reactions are very interesting. I will write down a few of them. This is the MgO this is a liquid plus corundum. I think this is somewhere there, leading to formation of Al2O3 plus, not this one, somewhere else, this one is the front. This will lead to formation of MgO Al2O3 and Al2O3, Al2 is a corundum, correct. And then the second one is basically liquid plus MgO Al2O3 plus, this is a ternary peridactic reaction, Al2O3 2 SiO2 leading to formation of 2 MgO 5 Al2O3 2 SiO2. What is this? This is 2 MgO SiO2. This is the one. This is the cotyride. So, cotyride actually basically form a ternary peridactic reactions. This is the one. Okay, this is not this reaction. This is this reaction. The cotyride formation is basically governed by this one, which is shown here. That is a ternary peridactic reaction. Now, and then there are many other reactions which I am not going to list it out. So, what you need to understand is that all this equilibria which I have shown you, this is the peridactic reaction which is getting transferred into the binary ternaries. Similarly, these eutectic reactions are also getting extended into the ternaries 1, 2 and 3, 4, 5, 6 eutectic reactions are present. So, there are like actually there are several more peridactic reactions which I am not listing out. Those peridactic reactions can lead to formation of sapphire and also some cases spinel, correct. So, but these are all available in the book. So, but you do not need to really study in detail. So, what you understand is basically from these lectures, from these things is that from the binaries to connecting ternaries, its only way of doing is by extending the binary phase diagrams in the 3D space model, and that is not always easy. In some cases, it is a direct translation of the binary phase diagram to the ternaries, like isomorphous systems or 3 phase equilibria where there is a eutectic reaction and 2 isomorphous systems. But the moment you have 4 phase equilibria existing in a binary in a ternary system developing, then things become little bit complex. That is what you see here even in this phase diagram also. The stainless steel phase diagram was very easy because it was only having it is the eutectic and peritectic reaction which are there present on the both the binaries are getting extended. There is no true ternary equilibria or reaction taking place inside this Gibbs triangle, but here the ceramic systems you have a lot of ternary equilibria getting developed. In fact, in this system there are 10 ternary new equilibria getting developed. So that's actually makes the life little bit difficult, but not so difficult in the sense that once you know the different phases which are forming, and because the phases formation in these systems are basically compound type, that is why probably it makes your life, it makes our life little bit more difficult, otherwise it is handleable. Okay. Now for the next 5 minutes what I am going to say you is that, because this is the last lecture, the real takeaway from this course is basically understanding the binary phase diagrams and to some extent understanding to some extent getting an idea how the ternary phase diagrams developed. Okay. I would not say that I have given you a complete picture of the ternary phase diagrams, because that is not possible, and that requires a lot of understanding of the topology and the space models, which is not there in our curriculum unfortunately. And so when I have tried to teach these ternary phase diagrams even in IIT Kanpur also, I had faced the problem that when I try to develop the space models, I always have difficulties making the students understanding the space model, what is inside it. That is because they do not have any idea how the phase spaces will look like. Remember there are many things actually. Those of you who do not know that when in a ternary phase diagram a two phase reaction and a two phase zone meeting a single phase zone, what will be the kind of intersection points is not dictated by the phase diagram specialist, it is dictated by the Landau rule actually. Landau has discovered a rule. So therefore, but they have discovered this rule without understanding the phase diagrams. They have looked at the topology of the spaces and then developing the rules. So that means what? To understand it, you need to go back to understand the topology. It's a separate mathematical concept which needs to be first understood, then only one can get into difficult phase diagrams and develop it. That is the first thing. Second thing is that, which you probably have taken me, is that all the ternary phase diagrams evolution, it depends on the binaries. Binary equilibria existing peritectic, eutectic, monotectic, syntectic, whatever, they actually, or the isomorphous type, they actually gets reflected in the ternary space model. That is how I have tried to discuss the lectures in my courses. So that means what? That means that this evolutions of these ternary phase diagrams is to some extent, or rather about 80 to 90% actually depend on the binary phase equilibria. So once you know the binary phase equilibria well, then you can actually understand these ternary reactions better way. The only things which you need to concentrate, if you really need to know the ternary phase diagrams which is required for ceramics and as well as the multi-component alloy system, is that you need to know the ternary phase equilibria, both the ternary eutectic as well as the ternary type 2 and type 3 type. One is the ternary quasi-vector and the ternary peritectic reactions. These two actually needs to be learned much better way. So for that one is to read the books and try to draw the pictures. That is what is been told Alan Spence in his book also, that if we want to really think in the 3D space, phase space, if you want to think, close your eyes and think in 3D space, you need to draw this diagram yourself, and then when you are closing your eyes, you can be able to think in the ternary space and try to understand how the phase evolution is happening actually in these phase diagrams. So that's about that. That's about the takeaway. Other than that, I have discussed you the binary liquid to solid state transformation, solid to solid state transformations in details. These are all very important. In many even colleges, I know these phase diagrams are not dealt with very seriously. They are just routinely done. Remember that metallurgists think in the terms of phase diagrams, equilibrium diagrams, and we connect the microstructure with the phase diagrams. So in between there is a gray area, what is known as phase transformations. So my aim is that in the next, if I get a time and if I get my chance opportunities I am going to deliver again another course on phase transformations, where these basic gap between the microstructure and the phase diagram will be bridged using the phase transformation concept. So, once you have this good idea about thermodynamics, phase diagrams and the phase transformations, also you will get a good idea about the metallurgical systems, and in between one is to also diffusion, because phase transformation depends on mostly diffusion. So, therefore, these are the 4 pillars of the metallurgical physical metallurgy, I would say, and to some extent mechanical metallurgy also, because phase transformation also dictates some mechanical behavior of material. So, phase thermodynamics and the diffusion are the main pillars, and in between lies the phase diagrams and the phase diagrams and phase transformation courses. So, once you have a good concept of these 4 courses, you can really go to the different level and make your journey much smoother in the research or the technological fields of the science and engineering or material science and engineering. Okay, thank you for your patience hearing, and these lectures will be available, I guess, to all the students in the different colleges, engineering colleges, as well also industry people, even after the course is over, because that is what is NPTEL concept is that even I have developed another course on NPTEL forum, which is now available on YouTube, advanced characterization techniques. Similarly, these lectures will be also available to you on the YouTubes. So, you can see it empty number of times. If you do not understand something, you can go back and read and look at the basic literature, because in the class, as there is no question answer sessions, so I keep on teaching, and I do not know how much you perceive it. That is what is a problem in this kind of online or video lectures. In the classroom course, you have always interaction with the students, even during the teaching also or after the teaching also, but here it is only possible after teaching by simply answering few questions on the forum, but there is no eye to eye contact in the class. So, that makes the gap between the student and the teacher much larger, and that is probably the problem. But at the same time, the takeaway from this course is that if you have not exposed to this course in your colleges to the extent I have done it, then this is going to give you a better understanding of the phase diagrams. Thank you.